So let's take a look at a couple of situations where we won't have a unique solution. It says to use Cramer's rule to solve each system if possible. Now that doesn't mean that I'm not going to solve it. I'm just going to try to solve it using Cramer's, okay, if I can. So let's go ahead and I'm going to go ahead and bring the 2y over to the left, and let me just rewrite this top one. I want both variable terms to be on the left. So I have negative 2y is equal to 6. Now here is my coefficient matrix. And I'm going to get the determinant of that, and that's going to be called my D. Okay, so let me get the determinant of that. So I take this right times this. That's negative 8. It's minus, and then this right here. 8 times negative 1 is negative 8. So that becomes plus, and guess what? That gives me a 0. That means that Cramer's rule is not going to work here. Okay? So Cramer's won't work to solve this thing. Okay? Can't use it. Why is that? Think about it. If I put dx over d and d is 0, that's why it won't work. Or put dy over d. So if the d is 0, we've got undefined and we can't proceed forward. So we can go forward with another way of solving it. So let's take a look. Let's go back to these two right here. What if I multiply this top row, meaning the whole left and right side, by a negative 2, let's say? So you can see what's happening, right? Cramer's won't work, but I can solve it a different way. Then now I'm going to have negative 8x, I'll put it way up here, plus 2y is equal to negative 6. And when I take that out and add the column here, I get nothing. Add the column here, nothing, is equal to nothing. Now, when we've seen previous videos, I've always said when you're trying to solve a system and the variables disappear, you need to stop immediately, right? Stop and ask the question, is that sentence that I'm looking at right here, is that a true or false sentence? Well, it's obviously true. 0 does equal 0. So it's true. That means that this system, because it's true, it's the same line. It's dependent. It's a dependent system. Now, what does that mean visually? It just means they're the same lines. How do we write the solution, though? Well, we write the solution this way. We say any x and y such that the relationship looks like this, right? Any xy relationship, as long as the relationship is this right here, it will work. We can't just say all real numbers because it's not any x and any y. It's any x and y that have this situation as their relationship. Then we have a point on those two lines, which happen to be the very same line. Okay? The two are actually the same thing. So let me give myself a little more room here for this next one. Let's take a look at this one. And again, I'm going to get this over to the other side, and I'll probably multiply through by 3 because I really don't want to deal with fractions. That's my personal preference to get that off. So I'm going to have negative 1/3 x plus, I need to move that over, plus y is equal to a 2. So I moved that over, it's become positive. I moved the negative 1/3 x, it's become negative. And here we go, there's negative x plus 3y is 15. Rearrange the order there. So I'm going to probably multiply through this top thing by 3. And I'm going to have negative x plus 3y is 6. So I'm going to probably put that in my coefficient matrix. So I have negative 1, 3, negative 1, and 3. Guess what? I'm going to call that my D. So here it is. The determinant, negative 1, 3, will be negative 3 minus negative 3. You got it. 0. So I can't use Cramer's. So what can I do? Well, I can go back to this scenario right here. I'm going to go back and rewrite, going back to the non-fraction, the non-fraction version. So let's take a look at these two green ones. I'm just going to multiply the top by negative. Okay? And when I do that, watch. Negative, negative, negative. So here we go. Add that, get 0. Add that, get 0. We get 0 is equal to, what is that, 9? So the variables disappeared. Immediately I stop sign. Why didn't I make it red? I don't know. Stop sign, and I ask myself the question, is it true or false? Is this statement right there true or false? 0 is equal to 9. It's false. Therefore, it's not the same line. They're parallel lines, which means there is no solution. There is no intersection point for those. And so that's how I actually write the answer. Okay? All right, so there are a couple of situations where we're trying to do Kramer's. We just can't because of the D. All right. So let's take a look at a couple more things, and then we'll be through. Determine whether the matrices are invertible. So we already concluded that in order for a system of equations to have a unique solution, then the coefficient matrix needs to be invertible. Okay? It needs to be invertible. And the only way it can be invertible is if the determinant is not a 0. So in keeping with what we just were seeing, let's take a look and see if these are invertible. Okay? In other words, is there going to be a unique solution? Okay? Can we use Kramer's rule, etc., etc.? Okay, now, so we have 6 minus negative 4, and good news, we can say yes, it's invertible. Okay, which means that the determinant isn't 0, which means there's a unique solution. We can use Kramer's. Okay, let's take a look at this next one. So this is going to be negative 3, negative 9, 4, 12. This is me getting the determinant. So negative 36 minus negative 36, and no. Now, look what the directions said. The directions said, if not, explain why not. Why isn't this matrix right here invertible? It's not invertible because the determinant, let's spell that properly, determinant is a 0. Okay? Alrighty, I hope this was helpful. Thanks for watching.